So humans want to go to Mars. However, a hidden enemy lurks in the shadows. Radiation. The Earth protects us back home, but on the journey to Mars, we'll have to pass through the Van Allen radiation belts. And that's not all. We'll also be exposed to intense cosmic radiation, solar radiation, and maybe even solar flares. Buckle in, because on this cosmic journey, the stakes couldn't be higher. But hold on, let's take a step backwards. You might be wondering, what even is radiation? What does it do to the human body? And how can we minimize this risk? Well, stick around, because we're about to answer those questions. We'll also explain why NASA's wrong about the dangers of space radiation, why it's best to travel to Mars during solar maximum, when the sun is most active, and how longer transits to Mars can actually lead to less radiation exposure. Many people think radiation will prevent humans from getting safely to Mars. What do you think? Are you one of these people? Well, whatever you think, let's find out if you're right. I'm Will, and this is Mars Matters.
Mars Matters.
Don't forget to like and subscribe. What comes to mind when you think of radiation? Perhaps the meltdown of nuclear reactors like Chernobyl and Fukushima, or maybe the radioactive fallout from nuclear weapons. These forms of radiation can be pretty terrifying, but did you know that you're likely exposed to dozens of sources of radiation every day? And I'm not just referring to getting too much sun at the beach or going for a dental x-ray. No matter where you live in the world, there are both man-made and naturally occurring radioactive elements in the air you breathe, the ground you walk on, and the food you eat. Whether we like it or not, radiation exposure is a part of everyday life. So what exactly is radiation? And will it prevent us from getting to Mars? There are two different kinds of radiation: electromagnetic radiation and particle radiation. Electromagnetic radiation is energy traveling through space as electromagnetic waves, whereas particle radiation refers to the presence of fast-moving subatomic particles. Despite sounding scary, not all electromagnetic radiation is dangerous to humans. For example, visible light, like the light shining off your computer screen or phone right now, is actually an electromagnetic wave. However, visible light makes up only a small fraction of the electromagnetic spectrum. Electromagnetic waves only become dangerous when they contain enough energy to strip electrons from atoms and molecules in our body. This creates ions that can damage our DNA, potentially leading to cancer. Only the most energetic electromagnetic waves are ionizing, while all particle radiation is. But what does all of this mean for future Martian colonists, who will be spending up to 3 years in the radiation environment of space? On a round-trip mission to Mars, astronauts will be exposed to a variety of both electromagnetic and particle radiation. They first have to travel through the Earth's Van Allen radiation belts. If they can get through there safely, they'll be exposed to cosmic and solar radiation during the 6 to 9 months it takes to get to Mars. And once there, since Mars doesn't have a magnetosphere or ozone layer, the crew will be exposed to high levels of radiation on Mars' surface as well. Then they'll have to travel through space in the Van Allen belts again on the way home. Each of these environments requires different strategies to keep the crew safe. Under NASA's current protocol, a mission to Mars would be deemed too risky if it exposes the crew to more than 600 millisieverts of radiation. This is much more restrictive than previous protocols, so let's go step by step through a round-trip mission to Mars and see if the radiation exposure received falls within NASA's career limits. The Van Allen radiation belts are zones of charged particles trapped in orbit by the Earth's magnetic field. There's an inner belt and an outer belt. The particles in the inner belt are primarily protons, produced when cosmic rays strike the Earth's atmosphere. The particles in the outer belt are primarily electrons, deposited by solar winds interacting with the Earth's magnetic field. Many people claim that these belts are too dangerous for humans to travel through safely, and even use this as an argument to suggest we never went to the moon. Well, let's see how dangerous these radiation belts actually are. Today's satellites have gathered valuable information about the belts, including what kinds of particles are there, how many there are, and what their energies are. However, this information alone isn't enough to determine the health effects during human missions, since assumptions need to be made about the length of time spent in the belts, which areas in particular are being traveled through, and what kinds of shielding the spacecraft has. But it gets even more complicated than that, since different particles have different effects in the human body, and factors like the age and gender of the person being exposed and which tissues are being impacted can have a large influence on the health effects of the exposure. Radiation risk assessment is a complex subject, so let's take a moment to break it down. This is Jim. He's floating in the Van Allen radiation belts. Let's figure out how bad things will be for Jim. First, we need to know how much ionizing radiation is present in the environment. Then we'll need to determine the extent of Jim's exposure to this radiation. His exposure will vary depending on how much shielding he has and how long he spends in the radioactive environment. Exposure measures how much ionizing radiation interacts with a given material or object, but it doesn't measure how much of that radiation is actually absorbed. Not all of the radiation that Jim is exposed to will deposit its energy into his body. Some of the higher energy radiation emissions are likely to pass right through him. For this reason, another measure is needed, called the absorbed dose. The absorbed dose tracks how much energy is deposited into an object, but it doesn't account for the type of radiation depositing this energy. This is an important omission, since some types of radiation can have worse impacts on the human body while depositing the same amount of energy. To account for this, each type of ionizing radiation has been given a radiation weighting factor, which is a multiple that's used to account for the presumed biological impact of different types of radiation on the human body. For example, energy deposited by alpha particles is deemed to be 20 times more harmful than the same amount of energy deposited by X-rays, gamma rays, or beta particles. Protons are given a multiple of 2, and neutrons are assigned different multiples depending on their energies. Once the absorbed dose has been multiplied by the weighting factor of the radiation involved, we've arrived at the equivalent dose, which can be used to determine the biological effects of the radiation dose received. There's another value, known as the effective dose, which uses tissue weighting factors to account for certain tissues being more sensitive to radiation than others. However, the radiation that makes it through the hull of a spacecraft would be deeply penetrating, and would affect bodily tissues fairly evenly, so we can assume that values for the equivalent and effective dose would be about the same. Now that that's out of the way, let's see how bad things would be for Jim. If Jim was unshielded in the most intense parts of the belts, he would receive about 26,000 rads per hour. This would be really bad, since it only takes 600 rads to be fatal.
Fatality.
So, how did the Apollo astronauts survive their trip through the belts? Well, for starters, this calculation assumes no shielding whatsoever. And thankfully, the radiation in the belts is very easy to shield against. We know that 95% of the rads would be from electrons, and most of the other 5% would be from protons. It only takes a few millimeters of aluminum to stop the vast majority of protons and electrons, and the walls of the Apollo Command and Service Module had 17 millimeters of aluminum protecting the crew. This was enough to stop more than 99.9% of the radiation from the belts. Practically none of the electrons could penetrate the hull of the service module, and only a few protons could. With 17 millimeters of aluminum shielding, the most intense parts of the belts would produce an absorbed dose of only 10 rads per hour. Even at high velocities, it takes about 1 hour to fly through the belts. So, since the Apollo missions had to go through the belts twice, does this mean that each crew was exposed to 20 rads? The 20 rad figure assumes constant exposure to the most intense parts of the belts, but the Apollo missions took a trajectory that kept them away from these areas. The belts aren't an impassable sphere around the planet. They're more donut-shaped, with the most intense radiation focused around the equator and barely any at the poles. In fact, thanks to an efficient trajectory and the aluminum hull, the Apollo crews made it to the moon and back with total mission exposures averaging less than half of 1 rad. The majority of this dose was from the proton radiation in the belts, and since proton radiation has a weighting factor of 2, we can calculate the average equivalent dose to be about 8 millisieverts. Health risks from such a small amount of radiation are practically non-existent. There would be no perceptible short-term effects, and conservative estimates for long-term effects suggest that less than 1 in 1,000 people would experience cancer in their lifetime from a dose of this size. Even then, in most cases, the cancer wouldn't be fatal. So, it seems that the Van Allen radiation belts aren't so scary after all. But this doesn't mean that the journey to Mars would be a walk in the park. Solar flares and cosmic rays can be a significantly larger problem, and can be much more difficult to shield against. So let's examine these in the next section. Jim would only receive 8 millisieverts of radiation from his 2 trips through the belts. This means that if he were one of NASA's astronauts, he could receive an additional 592 millisieverts before hitting his career limit. That may sound like a lot, but a round-trip mission to Mars would last for 2 to 3 years, during which time there would be constant exposure to cosmic rays and other forms of space radiation. On such a long mission, even small doses add up, so let's see if Jim can complete his journey without making NASA too nervous for his safety. Interplanetary space is filled with deeply penetrating cosmic rays. Despite the name, cosmic rays are primarily a form of particle radiation, consisting of atomic nuclei traveling at up to 99.6% the speed of light. These microscopic bullets will blast through almost anything in their path. But cosmic rays aren't the only threat in interplanetary space. Astronauts will also have to deal with solar radiation, such as solar wind, coronal mass ejections, and solar flares. Solar wind is a constant stream of particles emitted by the sun, while coronal mass ejections are large bursts of particles, and solar flares are bursts of electromagnetic waves. But how dangerous would this radiation be for Jim? 96% of the particles released by the sun are protons, so it's important to understand how easily protons can be shielded against. We learned in the previous section that despite having fairly high energies, about 99% of the protons in the Van Allen belts would be blocked by only 17 millimeters of aluminum. The protons in solar wind have much lower energies, so they wouldn't be able to penetrate the hull of a spacecraft at all. But coronal mass ejections release particles with a variety of energies, so it can be more difficult to predict the amount of damage they might cause. For example, let's take a look at one of the largest solar particle events in history. In 1972, there was a coronal mass ejection large enough to produce an unshielded dose of 4,000 millisieverts. But it consisted primarily of low-energy protons, so the dose could be reduced to 200 millisieverts by the hull of a spacecraft, or only 10 millisieverts by an onboard radiation shelter. Unfortunately, not all CMEs can be blocked so easily. The highest energy CMEs ever recorded occurred in 1956 and 1960. They were smaller than the event in 1972, but would have produced a larger shielded dose since high-energy particles are more penetrating. But NASA's guidelines allow for up to 250 millisieverts to be received from a single event. So as long as Jim was inside his transit vehicle at the time, even the most energetic CMEs would be considered tolerable. Unlike CMEs, solar flares produce electromagnetic waves, and waves respond differently to shielding materials than particles do. About 5 times a year, the sun releases a flare strong enough to produce an unshielded dose of 200 millisieverts, and a 2000 millisievert flare occurs about once a decade. Electromagnetic waves travel at the speed of light, so there's hardly any warning before they hit. And since solar flares only last for a few minutes at a time, it's not always possible to get to a radiation shelter before most of the dose has been delivered. So, what's the best way to protect Jim from solar flares? Well, the primary concern from flares is the release of X-rays, and the most effective material for stopping X-rays is one with a high atomic number, since large, tightly packed together atoms are good at absorbing wave energy. Aluminum, having an atomic number of 13, was sufficient to shield against X-rays during the Apollo missions, but stainless steel, like that used by Starship, will be even better. Steel walls only need to be 3 millimeters thick to stop 99% of X-rays, but they would need to be 25 centimeters thick to stop gamma rays. Thankfully, gamma rays make up only a small portion of the radiation produced by solar flares. But even if a solar flare does release a significant amount of gamma rays, or if a particularly large CME occurs, it's important to remember that solar radiation will always be coming from the direction of the sun. Therefore, by pointing the butt of the vehicle towards the sun during transit, the material in the engines, fuel tanks, and cargo will provide a very good shield against solar radiation. However, it won't be so easy to protect Jim from cosmic rays, since they have significantly larger energies and will be coming from all directions. Cosmic rays will be the largest source of radiation on the journey to Mars. But what makes them so dangerous? They're similar to solar radiation in the sense that the majority of the particles are protons, but that's where the similarities stop. Cosmic ray protons are much more energetic than anything we've discussed so far. They have an average energy of 300 mega electron volts, which is analogous to the protons released by the most extreme coronal mass ejections. And at the high end, they can have energies up to 10,000 mega electron volts. But remember, that's just the protons. The remaining 13% of cosmic ray particles have even higher energies. For example, the highest energy cosmic ray ever recorded was 100 million times more energetic than the particles in humanity's most powerful particle accelerators. Thankfully, these ultra-high energy particles occur very infrequently relative to their so-called lower energy counterparts. But what happens when a cosmic ray hits something? When cosmic ray nuclei come into contact with atoms in the shield material, both break apart, creating a shower of gamma rays, neutrons, and other particle fragments known as secondary radiation. In some cases, so much secondary radiation is produced that the absorbed dose to those behind the shield is larger than if there was no shield at all. This is because, without shielding, the primary particle would leave only a single ionization trail from passing through the body, whereas the shotgun blast of secondary radiation leaves multiple trails and deposits a lot more energy in the process. Fortunately, the weighting factor of secondary radiation is often much lower than that of the primary particle. Being struck directly by the primary particle would leave dense clusters of damage and break many molecular bonds along the trajectory through the tissue, but the damage from secondary radiation is much less dense and can be more easily repaired by the body. Therefore, although shielding cosmic rays can increase the absorbed dose, it can still result in a smaller equivalent dose by lowering the weighting factor of the dose received. The ideal shield thickness and composition for minimizing health effects depends on the energy and type of the radiation being shielded against. Unlike with X-rays, cosmic ray particles are best shielded using a material with a low atomic number, like hydrogen, to reduce the amount of secondary radiation that gets produced. Starship has a steel hull, so it won't be ideal for blocking cosmic rays. To address this, crew compartments could be lined with hydrogen-rich materials like polyethylene or water to help absorb the secondary particles. Now that we've discussed the radiation environment between Earth and Mars, let's calculate the dose Jim would receive during his transits. There are a number of different ways to get to Mars, and the method chosen can have a large impact on the transit time. For the purposes of this video, I'll be assuming a 6-month initial transit with a 550-day surface stay and then another 6-month transit home, since this seems to be the most realistic option for future human missions. If you'd be interested in hearing a more detailed dive into the pros and cons of alternative mission architectures, you should check out my other video, which I'll link in the description below. And if you're enjoying this video, don't forget to leave a like and consider subscribing so you won't miss out on future uploads. I always love to hear from you guys, so if there's anything you'd like to see me cover in the future, just leave me a comment down below. I'm definitely going to read and respond to every single one of them. But anyway, let's get back to Jim's journey to Mars. So if Jim spends a total of 12 months in transit, how much radiation would he receive during this time? The Mars Science Laboratory was launched in November of 2011, and it collected data on the radiation environment between Earth and Mars. While in transit, it measured a dose of roughly 1.8 millisieverts per day, with 95% of the dose coming from cosmic rays and only 5% from solar activity. This implies that the dose from a 6-month transit would be 330 millisieverts, or 660 millisieverts for the round trip. But is this an accurate estimate for future human missions? Well, the detector was located behind the heat shield, fuel tanks, and other mission equipment, providing it with an average shield thickness of about 16 grams per centimeter squared. That is about how much shielding would be present on a journey to Mars, but the shielding wasn't uniform. In fact, 30% of the field of view of the detector had almost no shielding at all, and much of the remaining portions were actually thicker than was optimal. An ideal shield thickness is 20 to 30 grams per centimeter squared, since less shielding allows low energy radiation through, and thicker shields can actually increase the dose due to the production of secondary particles. Therefore, with such an asymmetrical shield, the detector was impacted by both low energy radiation and high amounts of secondary particles. And to make matters worse, the transit was during a particularly weak period of solar activity. You might think that this would lower the dose received, but low solar activity actually leads to higher total radiation exposure. In fact, the effect of solar activity is so significant that during solar minimum, even an extremely thick shield would result in a higher effective dose than an unshielded transit during solar maximum. This is because most of the dose is from cosmic rays, and the sun's magnetic field can offer significant protection from these rays. But the strength of this protection varies as the sun goes through its 11-year solar cycle. During periods of high solar activity, the sun's magnetic field is stronger, reducing doses by up to 70%. Therefore, with an asymmetrical shield and weak solar activity, the dose recorded by the detector is likely a fair bit higher than would be experienced on human missions. Yet the 1.8 millisievert per day figure is often used to estimate doses during transit, leading to overestimations of the radiation risk. So, how much radiation should be expected? The effect of solar activity on cosmic rays is referred to as the sun's modulation potential. This value typically ranges from 400 to 1400 millivolts, with higher modulation indicating less cosmic ray intrusion into the solar system. The modulation during the detector's transit was only 580 millivolts, whereas the average modulation over the past 50 years was closer to 800. At average levels of modulation, the dose would have been about 25% smaller, or 60% smaller at the peak. However, since solar cycles are 11 years long, it's not always practical to wait for high modulation before launching a mission. Therefore, we should consider a range of possible doses during risk assessment. But we won't be able to extrapolate that range from the 1.8 millisievert figure, since it was calculated using outdated assumptions. The models used to estimate effective dose change over time as we learn more about how radiation affects the human body. Current models suggest that the daily dose from cosmic rays in space would range from 1.6 to 0.4 millisieverts, and that's without any shielding at all. Starship would have an average shield thickness of 20 grams per centimeter squared, and the portion facing the sun would be in excess of 100. At this shield thickness, solar radiation becomes negligible. But what about the dose from cosmic rays? Recent research suggests that a shield thickness of 20 grams per centimeter squared would result in a dose range of 1.2 to 0.4 millisieverts per day during transit. It should be noted that shielding reduced the dose during solar minimum, but didn't have much of an effect at solar maximum, since the sun's magnetic field and solar wind would have already eliminated the majority of the low-energy cosmic rays that shields are good for. Therefore, shielding is much more important during solar minimum than during solar maximum. In fact, it's been suggested that a different version of Starship should be used for each period of the solar cycle, one with 10 grams per centimeter squared to minimize secondary radiation during solar maximum, and one with 40 grams per centimeter squared to absorb low-energy cosmic rays during solar minimum. However, by adding a layer of polyethylene, a single version of Starship could be mass-produced that achieves low doses at any point in the solar cycle. A polyethylene-coated Starship would reduce the dose from 360 days in transit to only 140 millisieverts during solar maximum, or 360 millisieverts during solar minimum. Since NASA's career limit is 600 millisieverts, and about 10 millisieverts would be allocated to the belts, Jim would need to keep the dose from a 550-day stay on Mars below 230 to 450 millisieverts. Let's see if that's possible. So Jim finally made it to Mars. It's beautiful, it's magnificent, it's also being bathed in radiation. The Curiosity rover has been measuring radiation on the Martian surface since 2012. The measurements were taken from a low elevation, where the CO2 atmosphere provided 23 grams per centimeter squared of shielding. Unsurprisingly, it found that surface doses are a little more than half of a similarly shielded dose in free space, since the planet blocks 50% of all solar and cosmic radiation. From Curiosity's data, we can infer that an unshielded surface dose would range from 0.25 to 0.75 millisieverts per day, depending on the solar modulation at the time. For a 550-day stay on Mars, this means a total surface dose somewhere between 140 to 410 millisieverts. Therefore, if Jim were to launch during solar maximum, he could complete a round-trip mission to Mars without exceeding NASA's career limit. However, if his mission took place during solar minimum, some shielding on the Martian surface would be required. The atmosphere blocks the vast majority of solar particles, but most of the cosmic rays, UV rays, X-rays, and gamma rays still make it to the surface. But as long as you have a thick roof, that shouldn't be too much of a problem. 36 centimeters of Martian regolith piled on the roof would provide enough shielding to reduce the dose from cosmic rays by 50%, and 3 meters would reduce the dose by 85%. But that's only for the radiation coming from above. 15% of the radiation on Mars comes from the sides, since cosmic rays impacting the surface send secondary radiation in all directions. Thankfully, the polyethylene in crewed starships could be repurposed for use in habitats as well. A layer of polyethylene and a foot of regolith would be sufficient to keep exposures within acceptable limits, even during solar minimum. Of course, it's not realistic to stay inside all of the time. Jim may have to leave the protection of his habitat every once in a while. And what happens if a solar flare or coronal mass ejection occurs while he's outside? Since the atmosphere prevents solar particles from reaching the surface, CMEs would be less of a concern than solar flares. Most flares last for less than 20 seconds, which makes them difficult to avoid without warning, and the largest flares can last for several hours. For larger flares, a 50% dose reduction can be achieved with only 4 centimeters of a dense material, and 20 centimeters would eliminate up to 99%. Most spacesuits only provide a thin layer of light material, but an exploration vehicle with a roof that's at least a few centimeters thick should be sufficient to keep Jim safe. To put things into perspective, let's recap what we've discussed so far. NASA won't approve a mission to Mars unless total radiation exposures are less than 600 millisieverts. Jim's mission involves 2 trips through the Van Allen belts, 360 days in transit, and a 550-day stay on the surface. The belts would contribute less than 10 millisieverts, transits would contribute between 140 to 360 millisieverts, and the surface stay can be kept below 230 millisieverts with the use of Martian regolith for shielding. This means that a round-trip mission to Mars can be accomplished during solar maximum or solar minimum without exceeding NASA's risk margins. Okay, that's awesome. But how bad would it be if Jim did exceed his career limit? Come to think of it, how did NASA determine this limit in the first place? Canadian, Russian, and European space agencies have all adopted a 1,000 millisievert career limit, which is 67% higher than NASA's. Japan's is somewhere in the middle, having a range of limits that take age and sex into consideration. Age and sex play a large role in determining cancer risk. Young people have long lives ahead of them, so cell damage has much more time to become cancerous, and women's organs tend to be more sensitive to radiation exposure. NASA used to take age and sex into consideration, but in 2022 they decided to change the limit to 600 millisieverts for everyone. So why did NASA make this change, and how was the new limit chosen? 600 millisieverts is the dose at which a 35-year-old female would have a 3% risk of dying from cancer at some point in her lifetime as a result of the radiation exposure. This isn't the risk of dying from cancer during the mission. The 3% risk includes death at any point in time after the mission, so long as the death is in some way connected to the exposure. Even in a worst-case scenario, it's extremely unlikely that anyone would die from radiation during the mission. In most cases, there wouldn't be any long-term complications at all, and if there were, they likely wouldn't occur until old age. To put that risk into perspective, research from the Canadian Cancer Society suggests that up to 50% of all smokers will die from smoking-related illnesses. So if a journey to Mars resulted in a 3% likelihood of dying from cancer, that's still more than 15 times safer than taking up smoking. In fact, it's been stated that if you were to send a smoker to Mars without their cigarettes, it would actually decrease their cancer risk. So NASA's risk tolerance is fairly conservative. But then why did they decide to reduce the limit? When the 3% risk was calculated on an individual basis, it led to young female astronauts having lower career limits than their older male peers. Therefore, in 2021, a committee led by Hedvig Hricik proposed that the same standard be applied to all astronauts for the sake of equality of opportunity. This either meant that limits had to be increased for young women, exposing them to higher than 3% risk, or decreased for everyone else, limiting the time they could spend in space. Of course, NASA decided on the conservative approach. Some people worry that NASA's conservative approach to risk management will cause it to fall behind when it comes to exploration and colonization efforts. To avoid this, it's been proposed that individuals could sign a waiver in order to exceed their career limit. But would it be safe to do so? Much remains unclear about the health effects of chronic low-level radiation exposure. Current models are based on data from atomic bomb survivors who received large doses over a short period of time, but dose rate has a large influence on the resulting health effects. The body has mechanisms designed to find cancerous cells and remove or repair them, and these mechanisms activate in response to radiation exposure. It's been theorized that at low enough radiation levels, the benefits from the activation of these cancer-fighting mechanisms can keep up with or even outpace the negative effects of the exposure. It's been heavily debated whether there exists a threshold dose below which the body can repair itself faster than damage occurs. If a threshold does exist, it could be possible to receive even large radiation doses safely so long as they were delivered over a long enough duration. Despite this possibility, NASA and its international partners use the linear no-threshold risk model for radiation exposure. In essence, the LNT model ignores dose rate considerations and repair mechanisms. It's assumed that radiation exposure and cancer risk have a linear relationship, such that a given quantity of radiation will have the same effect on the body regardless of how fast it was absorbed or how much other radiation was absorbed with it. It's also assumed that there's no such thing as a small enough dose to be considered safe. This makes it easier to enforce safety guidelines, but compromises on scientific accuracy. It's quite possible that the low dose rate during space exploration would allow the body to repair itself before damaged cells could become cancerous, but it's too early to say for sure. NASA is aware of the limitations of the LNT model, but there just isn't enough data on low-level radiation exposure to reliably establish a threshold. For example, we know from atomic bomb survivors that an acute dose of 1000 millisieverts results in a median lifespan reduction of about 1 year. But what if someone received 1 millisievert every day for 1000 days? The LNT model would conclude that, regardless of the dose rate, the result would be the same. But it's well known that health effects are much less significant or potentially even negligible at low dose rates. To account for this, NASA applies a dose and dose rate effectiveness factor to their risk calculation, reducing the assumed cancer risk by 33% for chronic exposures. Although that's a step in the right direction, analysis of the available data suggests that NASA's blanket 33% reduction is both too small and too imprecise to be basing policy off of. For example, it's possible that the dose rate from radiation in space is low enough to be repaired by the body before lasting damage occurs. If future data confirms the existence of a threshold, it would revolutionize our understanding of the risk of space exploration. But even if we ignore dose rate and thresholds entirely, and assume that the total dose from a 3-year Mars mission were absorbed all at once, studies on acute exposures suggest that the median lifespan reduction would be less than 1 year. Therefore, if you're lucky enough to see Mars become a vacation destination in your lifetime, you should feel pretty safe taking the trip, at least as far as radiation is concerned. But even if the radiation isn't going to kill you, couldn't it still cause other health problems? It's widely believed that even minor radiation exposure can lead to high rates of debilitating diseases, and that genetic defects can make their way into the children of those affected. However, data from the Hiroshima and Nagasaki bombings doesn't support these beliefs. When the lifespan of 120,000 survivors was studied, it was shown fairly conclusively that even an acute dose of 1000 millisieverts has very limited detrimental health effects over the course of a lifetime. Additionally, no genetic effects are detectable in the children of irradiated individuals. 77,000 children of survivors were studied over the last 80 years, and no detectable radiation-related pathology was discovered. One exception to this finding is the effect on babies exposed to radiation while in the womb. Therefore, safely navigating Martian pregnancies will require additional precautions, but surface habitats shielded by Martian regolith are capable of reducing radiation exposures to Earth-like levels. So it should be possible to procreate on the red planet without having to worry about radiation. It's clear that the risks associated with low-level radiation exposure have been drastically overestimated. Regardless, research is being conducted around the world to help mitigate these risks even further. For example, NASA is investigating the use of dietary supplements to combat the effects of ionizing radiation, and medical advances continue to reduce the death rate of various cancers. Therefore, despite already being low, the radiation risk of a mission to Mars should continue to decrease over time. In the future, we could develop cycler spacecraft that are robust enough to protect against cosmic rays, assembled piece by piece in orbit to provide a safe and luxurious transit between Earth and Mars. However, such fantastical solutions shouldn't be necessary to deal with the radiation challenges of Mars colonization. To drive this point home, let's take a moment to recap some of the things we've discussed so far. Whether we go to Mars or not, radiation is a part of everyday life. As a result, our bodies are constantly searching for and repairing damage to our cells and DNA. Large doses can overwhelm these repair mechanisms if absorbed too quickly, but the dose rate in space could be low enough to be managed by the body. However, space agencies choose to endorse the assumption that even the smallest of doses can have lasting health effects. This belief has led to career limits that are so conservative that even if an astronaut were to receive the maximum dose, it would still be many times safer than taking up smoking. Thankfully, with the implementation of a few simple strategies, these limits won't prevent a journey to Mars. In the long run, it's likely that habitats and transportation vehicles can be constructed that will eliminate the radiation risk completely, allowing for long-term habitation and even procreation on the red planet. But even before this infrastructure is in place, astronauts should be able to complete a round-trip mission without exceeding even the most restrictive of exposure limits. Radiation is invisible and scary, and it's been portrayed by the media as having much worse effects than it actually does. We naturally fear what we don't understand. Before the Earth was well explored, map makers would populate unknown regions with dragons, ready to consume any who dared enter their territory. Rawr. The dragons may have been imaginary, but even imaginary dragons can and did prey upon the minds of would-be explorers, and in doing so, stifled human exploration for centuries. Today, the journey to Mars is filled with dragons too. It's been said that, to avoid the radiation-infested seas of space, ultra-fast spacecraft will be needed to get to Mars and back in impossibly short times to ensure a safe voyage. Or that only ridiculously massive spacecraft can provide sufficient shielding to protect from cosmic rays. There's still a lot to learn about how the body responds to low-level radiation exposure, but preliminary evidence seems to suggest that radiation isn't quite the dragon we once feared. If you enjoyed this video, consider subscribing, as I'll be addressing the other dragons standing between humans and Mars in future uploads. What about going to Mars would scare you the most? Let me know down in the comments. Thanks for watching, and stay curious about Mars Matters. But this doesn't mean that the journey to Mars is a walk in the park. Solar flares and cosmic rays can be So it seems the Van Allen radiation belts aren't so scary after all. But that doesn't mean that the journey to Mars is a walk in the park. Solar flares and cosmic rays. So let's examine these in the next section.